I've had a number of new subscribers recently, and it's been significant growth even for my small numbers. So welcome to everybody, and I hope that you find value in these videos. I'm trying to provide as much detail as possible as I go through this process and not present what I call happy path, meaning that everything works the first time. There's not a lot of work I do in the background to prepare for each of these videos. I don't pre-cut wires. I don't pre-fit on the board other than maybe just making sure that I need two boards or I can fit it all on one board. But I don't pre-lay everything out or pre-assemble everything or pre-test everything so that I can demonstrate a working product. I hope that is what you're looking for because you're going to see the good, the bad, and the ugly in my video series. Another quick administrative note here is I'm actually being pulled away again. Unfortunately, I've got a couple of major projects that have kicked off at work, and that takes me away from my desk every once in a while. And once again, I'm going to be away from my desk again for a week. And I've got some footage for something else that's already done. I just need to edit that, and time permitting, of course, time is key. Time permitting, I will get that edited up and try to get something released while I'm on the road. We'll see how that works out. And while I like to record my introductions with my face, because I am in between two trips that were very nearly back to back, I am doing an intro here just as a voiceover. So today I want to test the control logic and timing and see how the timing of the actual breadboard compares to what my expectations are. Here we go, let's get into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Okay, I've got my control logic out today, and I've got my clock hooked up so that I can drive the signals on this circuit. And what I've done down here is I have tied all of these inputs low, because if I don't tie them all low, I end up with garbage that comes across here intermittently, and I don't want to see that. I could potentially find something here that did that. Yeah, I don't want to see the floating values coming across from the CMOS related chips here. So I've got everything tied low. Let's test this. First thing I want to test here is the symmetry of my clock signal. I am basing a lot of my assumptions later on through this build with the control logic to be based on the clock signal being exactly inverted, no delay between the inversion. So I'm going to take the yellow trace, which is, since I don't have yellow bands here, I'm using a red band. And I'm going to plug it into where my clock signal is, and then I'll attach that to ground. What I have here is my nice square wave associated with that clock signal. I'm going to save a picture of that just so I can present it up on the screen. And I'm going to change my trigger to be on channel 1 on the rising edge. And where is my trigger? Let's speed this up a little bit then. This cheap tablet type oscilloscope has its challenges. I'm triggering on the rising edge. Here's my trigger. Here's my trigger point. This is when the trigger happened. I'm triggering on the rising edge. And then now let's add in the inverted clock, and that would be here, and then get ground on that as well. And this looks really good. This looks very symmetrical, like the lines are actually overlapping. So let me zoom in here. So at 50 microseconds per division, that still looks exactly dead on. 20 microseconds, 10 microseconds, 5 microseconds. Now we're getting into the nanosecond range, and you're starting to see where it actually crosses. But it looks like they are dropping at the same time, and that looks very symmetrical in that the two traces happen to cross at exactly the same spot. Let me try the falling edge, and there's a little bit of a mess with this trace here, and that's probably going to be due to my setup here and nothing more. But those appear to be starting their travel pretty quickly, pretty close together. this bounce down here is related to the ground setup I've got over here. So I'm not going to try to solve for that. As I zoom in, that looks very glitchy. Now, is that... You know, the question is that my setup or is that my... It looks a little bit better. Slight delay on the rising edge. I'll get a picture of that. But every once in a while it glitches out over here. But if I get down into the 500 nanosecond range, those look like they're overlapping beautifully. How can I improve my measurement? One way might be... see what I can do here. Take the ground lead off, take this off, so now I have a probe. And this band here is where I should be able to put a spring. Here's the problem. This is so cheap that they did not send springs. I don't have springs for this these probes. So let's see if we can make one. Here's a piece of hookup wire here. And then I'm going to strip and pull the wire out so I have a piece of bare wire. I just happen to have, this is hexagonal, so it's not ideal, but it should work. And I'm just going to bend this as tightly as I can around this. Now, the key to this particular mandrel, if you will, is that it is slightly smaller, I believe, than this on the probe. And I have it, I just happen to get this. So if I slide this on here now, and if I stick the probe here and ground it there. Well, I can't ground it there, so let's ground it here. That should give me a cleaner trace, in theory. Let me see what I can do here with this one. Okay, so there's that. There's that. I should have my two signals. They clean up pretty nicely, but I still have just a hair of noise here. And it's not quite as perfect on the falling edge of the clock, the rising edge of the inverted clock, as I would like it to be. Still noisy over here. But that seems to be a great signal there. This is just slightly delayed. So I'm not quite as perfect as I'd like it to be. So let's stop that there. Let me pull some time cursors out and slide this over to my trigger point. What am I measuring from? Let's see here. So I'm measuring from that voltage where that trigger point is on the falling edge to that about same location on the rising edge, and I'm at 5 nanoseconds difference. That's more than I'd like it to be, but I think it's far better than it would be through an inverter. So what's going on down here? What I have is I have all of these lines, signals pulled to ground, and I pulled a couple of those signals out so that I had room to hook in my probe. So if I reattach these back to ground, that noise over here will stop. Well, with that, the next thing I think I want to do is, in reference to the clock signal, I want to see what my other signals look like. This, I believe, was my assert. I don't have anything programmed here. I can't measure that. So the problem is this is not triggered by any clock and nothing's going to change it. So that's not a good signal to measure. On the other hand, let's do this one. This is a good signal to measure against the clock, because this should be the and lat signal, which should only be active on the clock signal. And you notice they're overlapping here. So they're exactly the same signal, at least at this resolution. So if I measure the difference between when they start to fall, I have 35 nanoseconds. Can I improve that? Let's see here. So my buffer is delaying that signal by 25 nanoseconds. I am currently delayed by 35 nanoseconds. So if I was to take and remove the buffer and let this run again, so this is the signal coming off of here. Let me stop again and line up these cursors again. I changed my resolution. That does not change the time. Okay, that's got me confused, because that tells me that this signal and this delayed buffered signal are, the buffer adds no delay in this, or far less of a delay than I was thinking it would. Now I'm looking at LS series logic here, and does that make a difference? Okay, no, I think I'm measuring the wrong thing here. So thinking about this, I am taking the, I'm taking the delayed clock, not the actual input clock, but the delayed clock, and measuring against that. I am measuring the correct thing. I'm gonna have to think on this a little bit. I don't know that I have a solve for this today. Okay, so this is interesting. What I've done is I went through and I added the LS logic here, and there's a pretty varied difference in some of the timings. And NAND gate is actually 10 nanoseconds faster than the HCT, and the inverter is 9 nanoseconds faster than the HCT. So when I'm looking at this and latch signal, I end up with a 10 nanosecond difference between the two, and the HCT logic is actually going to be the slower of the two. Now, does that explain the 30 odd nanosecond, 35 odd nanosecond delay that I'm seeing? Not completely, but it does explain some of it. As I go back through this and consider what I'm looking at here, coming off of here is my clock signal, which is my enable. And I actually pay a -1 nanosecond penalty, meaning that I actually get a gain in this case. Difference in how they're implemented. A gain of 1 nanosecond by having this clock enabled. And then the propagation delay is 39 nanoseconds, which is 6 nanoseconds faster. So now I'm 7 nanoseconds faster than the HCT logic. We're talking about 53 versus 38. That's, is my math right? It doesn't seem right. 53, 38, that's 5 nanoseconds faster. And then after that, I have this buffered through this XOR gate, which is a 5 nanosecond difference. So there's the other 5 that makes up 10. Now these are worst case I'm looking at in all of these. So perhaps I should be looking at typical performance instead of worst case performance, because right now I may be getting more typical performance than worst case. Again, I think I'm going to have to think on this. I may not have a solve today. Okay, for me it's the next day. For you it's probably just a few seconds later. And there's a couple of things that I have done in this spreadsheet and a little bit of research that I've done in order to improve my analysis here. The first thing was I had HCT in here, and in reality it was HC logic that I had done the research against, but I had incorrectly labeled that. So that label was incorrect previously, and I have corrected that now. The second thing is that this clock enabled does not give you a benefit if you are only changing the clock enabled, or changing the clock enabled in conjunction with the actual inputs. What it does is it's going to end up being the maximum of either the inputs changing to the outputs or the enable changing to the output. And right now I have negative numbers in there. There's no performance benefit to be gained by using that clock signal. What it shows on the spreadsheet implies that there's a performance benefit, and I have to reorganize the spreadsheet a little bit in order to represent that. Right now, the way the spreadsheet is architected, I need to use the negative numbers because on the breadboard, I am only using the enable. The actual inputs themselves are not changing with each clock. So I want to make sure that I call that out, that this column here is not totally correct. So I'm going to have to re-architect this to get me the right information as I go forward with these signals. The original line that I was working with is here. The LS logic line that I added in the prior segment is here. And then I went back and I actually found the typical performance for each, and I have those listed out here. And if I look at the and latch portion of this, the LS typical is 32 nanoseconds. Well, that delay actually looks very close to what I was observing on the breadboard when I was measuring it with a scope. So that makes me feel a little bit better that I'm actually getting the numbers that I should be getting, or the delays that I am expecting. I just happen to have been expecting the wrong thing as I started out. So I had to go and check my expectations against my observations and make sure that those were correct as well. So this does now bring up a good point that I want to make. I set out at the beginning of this trying to predict what my results were going to be, and then I measured my actuals against my prediction and had to spend some time trying to reconcile the differences. I believe it's a good thing to do, to make a prediction, or at least try to understand what it is that you are doing and figure out how to measure your work against what your expectations are. And if there are differences, sometimes maybe your thinking is wrong going into it, and sometimes maybe you've done something wrong and then you need to turn around and go back and change what you've done. I've had to do both of those now. I think this was a good exercise. I think I ended up coming out better for this because I was able to explain to myself anyway. I may not have done it quite so well in the video, but I was able to explain to myself what I was seeing. It now gives me the baseline that I need going forward, where I can look at the typical performance rather than the worst case performance, because I don't believe that we are going to be operating near worst case. So here's where my head was. I was thinking typical was going to be interpreted as ideal, and nothing ever works under ideal circumstances. That was probably incorrect thinking, and I know now that I should have been looking at the typical performance numbers rather than the worst case performance numbers. And so I will update my spreadsheet as well to address that, such that these numbers will probably go away. Of course, I'll correct this, and then I can start looking at just the HC and the LS typical performance so that I can measure against those. Yeah, worst case might come into play a little bit here and there, but it will be very infrequently when that happens. Thank you. We'll see you soon.